Hello everyone. In this video, we are going to continue solving the dual problem. I'm just going to remind you what we were looking at in the last video. So we have the dual here, which we got after solving for W, B, and Psi. This entire thing here, or maximization subject to constraints, right? So this is the entire thing that we need to solve. To solve this, we're going to introduce an optimization algorithm. So this algorithm is similar to gradient ascent. It's slightly different and it's called coordinate ascent. In coordinate ascent, we consider the unconstrained optimization problem, which is just this guy here, max of alpha over W alpha 1 to alpha m, right? So all the alpha, you're going to find alpha which maximizes this expression. Now we know that W is a function of all the parameters alpha i's. Now the algorithm for coordinate ascent goes like this. For I is equal to 1 to m, we find the argmax of alpha I, only alpha I. Solve for one alpha at a time. And then re-optimize W with respect to alpha I. So we solve in gradient descent, we take the gradient and then take one step at a time, right? Similarly, we solve for one alpha, one of a number of parameters that we are looking to optimize, and then we substitute that back, and now in the light of the new information, new updated value for alpha I, we hold some other subset of alphas constant and then optimize another alpha I. So we continue this until none of the alpha i's change value and we return the alpha i's. So this gives an efficient way of solving the dual problem, and it's simple enough to implement. Now, let's consider the SVM dual optimization problem. Specifically what we want and whether coordinate ascent in its simplest form that we just saw can be used for the SVM dual problem, or do we need to make some minor modifications. So let's look at the dual optimization problem. So that's right here, right? Now, for this problem, for our problem in question, can we hold all the alpha i's fixed and only update one alpha I? So suppose we are going to only update alpha 1 and we are holding alpha 2 to alpha m fixed. And would that be possible to just hold one and to update one and hold the other all fixed? The answer to this question is no. Now think about it. We have a constraint here, an equality constraint, which comes in the way. So if we just isolate alpha 1 here, let's say alpha 1 y1 is equal to sigma I is equal to 2 to m minus of alpha I yi, right? So this quantity, because we are taking all other alpha i's except for one to this side. Now we can multiply both sides by yi. We will get that this yi will go to the other side, and alpha 1 is exactly defined by this quantity. So it's not a guessing game. We know exactly alpha 1 in terms of all other alphas. Now which is why we can't update one alpha without updating other alphas, right? So since alpha 1 is exactly determined by the other alpha i's, if we had to hold alpha 2 to alpha m fixed, we can't change alpha 1. Now that's why the coordinate ascent algorithm cannot be directly used, but still there is hope. We could make some minor modifications and still apply coordinate ascent. Now how do we do that? We just make a very simple modification. Instead of updating one alpha I, we update two of them at the same time. So this is called the SMO Coordinate Ascent Algorithm. And when you look at Veka or Scikit-learn or any other platform, you generally will get the SVM classifier would be mentioned by SMO, by the optimization algorithm. So that's what is this. That's what we are learning here, the SMO Coordinate Ascent Algorithm. So when we reach the dual form, so we solved the primal, solved for WB and Xi, and then we reached a dual form, and then we want to solve the dual form now for alpha so that our entire SVM optimization problem is entirely solved. And for that, we use a specific variation of coordinate ascent applying by updating two alphas at one time, and that is called the SMO Coordinate Ascent Algorithm. And now we repeat until convergence, select some pair of alphas, alpha I and alpha j, to update. And oftentimes, so this is the high-level version of the algorithm, the simplest detail that will allow you to understand the general algorithm without going into too many specifics. So there is usually a heuristic that helps you pick which alphas will give you the maximum progress toward the global maximum, right? So you want to select the alphas that will need to be solved first so that you make maximum leap to your convergence. And usually a heuristic is used there. And re-optimize W of alpha with respect to alpha I and alpha j, while holding all other alpha k's, which where k is not equal to j, comma I fixed. So you can see that this algorithm is very similar to coordinate ascent, except that you're doing two at one time. And now the update to alpha I can be computed efficiently. So this is fixed. So now this is exactly what you need to solve, right? So you are, instead of solving all the alpha i's, you are getting rid of all the k's where k is not equal to j comma I, and then setting this quantity to a fixed number and solving for that. And that is what the SMO algorithm would do to finally finish solving SVMs.